All right. How about we go ahead and get started? Welcome back from break. Hi, everybody. How was your break? Are you even in this class? There's an $18 charge to sit in. Cash? No. All right. So everybody did have a good break? You spent the whole time working on linked lists and pointers? No, liars. All right. I'm just going to tell you last time I sucked because I didn't have officers. I still suck. I will not be able to have my office hours today. I'm consulting on a legal case, and I have to be deposed tomorrow, which means I sit in a room all day and have lawyers ask me questions, and so the lawyers want my time today so that they can review my material beforehand. So if you have questions, we're going to have a question period now in the beginning of class, and I will do my best to answer them. Otherwise, you can email me, or even preferably, if you have a question, post it on the project forum on Blackboard, right? If you post it there, I get an email with the question. I'll do my best to answer it quickly, and you'll be helping out your classmates by, by asking a question they might have been asking, and then the code will be public. All right. All right. Any questions before we get started? Project questions, yes, sir. Today, probably. The other professor who does the rubric emailed me, and I emailed him back last night, so it should be shortly. So, yes? For the constants, yes. I have queried the TAs about, and the other professor about the constants and use of constants. So in the rubric that I saw, there were constants for the next project, and I asked them, like, what did you have in mind for those? And if we don't have any, can we just use the points for something else that's harder? So.
Are we allowed to change the class definitions that
Are you allowed to change the class definitions? Why would you want to change my perfectly wonderful class definitions?
Because the .add_refugee function
Mm-hmm.
takes an operation, and if I want to use it in the file...
Wait, the .add_refugee takes a what? The .add_refugee method takes a...
Operation. It's used on operations, yes?
It's used on
The operation class.
the operation class, yes, uh-huh, uh-huh.
So...
It's used by the operations class.
Yes.
Got it, okay.
So that's...
Uh-huh, yes,
within the load file method,
yep.
if I want to use the .add_refugee...
Yeah, you don't need to use that in there. Or you can. I used it. So here, yes, so finish your question. So let me rephrase your question as it stands so far. In the operations class, there is a private data member, a private data method called add_refugee that's not public. And you want to...
Well, if I don't use it in the load file
Uh-huh.
method, where would I use it?
In the load file method.
So if I want to use it in the load file method,
Uh-huh.
would I have to then declare an operation object in the load file method?
No, you don't, because, so the question was, if to use the add_refugee private method in the operations class, do you have to call that on an operation object? And the answer is yes. But remember, inside the load file, that is also inside an operation object. So if you just say add node or add_refugee without saying dot something, it applies to the current object that you're operating inside.
So the code would literally just look like dot.
So the code would essentially look like this. Ready? I'm going to say it really fast. Okay. The line before the while loop, you would say something like refugee star current refugee equals new refugee, open close parentheses, while in file into angle angle star refugee close, right? And then inside there, you would have add node star refugee, and it would dereference it. And there I just wrote your whole function for you. It's like 3 lines of code. And then there's some curly brackets. Fortunately, I went fast and no one ever got that. Oh! I figured that's the hardest part. I figured there'd be questions about that anyway, so I wanted to give you a hint about that. But the answer is that here's what you're doing in the load file. You create a refugee using the new refugee. New function, right? Refugee. Create a new one before the loop. Okay? Because when we read from the file, we need a refugee to put things inside. Okay, so before the loop, you create a temporary refugee. Inside the while loop, you use input file angle angle, and then that refugee, which is like current refugee or temporary refugee or whatever. But the trick is you have to put a star in front of that to dereference it. Because what you're saying is input file into the refugee that's at this address. Okay? And once you have the overloaded operator working, it just works. It's beautiful. And it works just like all the other input we've done all semester with the angle. The trick is that you have to put the star in front of it. You create it using new, and you put a star in front of it. Then inside the loop, what I used this private method add refugee, and I just said, hey, add this refugee, and I gave it the current refugee, and it added it to the list. The reason I did that is because now I have a little method called add refugee that adds the refugee to the head of the list, and that's separate code that lives by itself. Even though it doesn't get used anywhere else, it's just a convenient thing to add something to the head of the list. Okay? Then after that, I have another line saying current refugee equals new refugee, because you have to make a new one to hold the next thing coming in. A common mistake people make when they're loading the file in is that they will create one refugee object using new, and then they will like keep putting every current information into that one refugee and then adding it to the list. So the list only ends up being one thing repeated over and over that has like different data in it. So, yes. Okay, you did it differently. There's other ways to do it. No, you don't have to do it. Yours has to work. That's all. It has to work. It doesn't have to be exactly my algorithm. Part of this class is you developing your own algorithm. That would be like asking an English teacher. I already wrote my essay, and it doesn't use the same words yours does. So, and I don't know. I haven't taken any English classes. Does that make you fail? No, you don't even have to use the add thing if you don't want. It's just a convenience. And the reason I like to do it is because say at some point later on we decide that we're annoyed that when we put things into our linked list by putting them at the head, the list comes out backwards, right? And we want to go, oh, it would be nice if we could put things at the end of the list, and that way they would come out forwards when we printed them. Instead of having to look through all the code and find every place that you're just manually adding something to the head of the list, all we do is change that one small function, add node, and you make it add to the end instead, and it changes everywhere in your program. So it's just kind of how I prefer to structure my code. Sir?
Just like theoretically, if you get the vectors to work, or not the vectors, the operations to work,
Yeah.
it's the same, like your menu function will be the exact same.
So the question is, if you get the operation stuff to work, is the main function the same? And actually, the answer is pretty much almost identical. So pretty much almost identical. So because you're making, didn't we make the calls pretty much the same, like the methods and the same? So you're just operating on operations. That's what we did last time too, right? So main, I don't even know that main needs to change at all. It shouldn't. Yes? Do you need to have a destructor? I don't believe that's part of the rubric. I wanted to show you one before just so that it did two things when I showed it to you before. It showed you that it was called, and it was another example of how to traverse the list, but in a slightly different way than we'd have been. So I don't believe it's part of the rubric. If we do need one, it's almost identical to the one we did in class, so it's not like a huge imposition. Other questions? Make sure my cell phone's turned off. Yes? Uh-huh. How do you call name search? It's in the operation. Oh, in the name search thing? Okay, so let me ask, so let's pretend when you have a refugee, right, you're iterating over the list, and you have like a current refugee, which is a pointer to the current refugee. Does that make sense so far? You have a pointer, you have a linked list. Every refugee doesn't have a name, does it? No refugee variable has a name. It has a last name and first name stored within, but each one of those objects doesn't have a name. Instead, you have a pointer to it, which is the address of that. If you want to ask one of those refugee objects if its name matches, you need to have a pointer to it. So just like we had the iterator that goes down that linked list, like we did last class, you iterate over the linked list. So you say something like current equals head, while current does not equal to null, open curly brackets, and now you have the pointer to something. Then you say, if current arrow name search, and then the parameters in there, equals true. So you use the pointer and follow the pointer operator, which is the arrow. And when you get to that object, you say, hey, is this your name? And then the object will either answer yes or no. It sounded good to me, but looking at your face, we kind of lost you around the pointer part. So you iterate over the list with the pointer. Just like we had the vector before with square brackets dot something, now we have current arrow. So before we had like whatever the vector name is, square bracket I dot something. Now we have current arrow, and then you call the same method. So what's changing is not the way that we're doing the name, asking the name. What's changing is the way we are storing and iterating across all of the different refugee objects. Yes? Uh-huh. Yep. I would, and I would say exactly. So say we did like, current arrow name search equal true. The next line would literally be cout angle star, because we need to follow the pointer and dereference the pointer, current. That's it. And ENDL if you want, end line. So the nice thing about the overloaded input and output operators is things work like we were used to. The weirdness of it is because we have pointers, we have to keep track of whether something is a pointer, which is an address, or the dereferenced pointer, which we follow either by doing the star or the arrow operator for calling a method, which gives us an object. And we're going to have a practice problem about this stuff today because I know it's a novel concept, to put it politely. Other questions? Yes?
What is secondary on your website,
I need a little more context for your question. Like overloaded the input and output operators. We went over that for the point class. And so if you look back on I can't remember the date, 12th or 14th. It's in there. It's in there. I emailed someone with the exact date last night because I looked it up. It's like the 12th or actually the 14th, the 2nd or 4th or something. But it's in the point class. Look for a file in the code directory that I showed. It's point2.cc back from one of the earlier days. Here, I can find it really fast for you. So it was April 1st, it's actually April 1st and 3rd, one of those 2 days. So if we look at this, we show how to define it. And if you need to go back and look at the... What? It's not. Why didn't anybody email me and let me know? No, I wanted you to have that. Well, I know the video's on YouTube, but I meant for you to have the code as well. I didn't realize the code for the 3rd wasn't up. I will put it up when I get a chance today. Okay? In fact, you know what I'll probably do is I'm going to give you some practice problems. I will upload it right now during class, so you'll have it after class, after we have other questions. Other questions? And I'm sorry about not uploading that. If something's not there, email me. So, anything else? Sir?
Is it possible for there to be any information in a TXT file that's not visible?
The question is it possible for there to be any information in a TXT file that's not visible? And the answer is absolutely. Yeah. So, and you'll get into trouble if you do things like cut and paste from the screen to a TXT file, because there's end-of-line markers and hidden formatting stuff that you can't see. If you want to work with a TXT file, the safest way is to just download it straight from my website by clicking the link and then saving it, rather than cutting and pasting. So, do you have some sort of error you suspect is related to? It's by your right foot. So, other questions? Going once. This is a challenging project, right? How many are mostly done? Anybody? Oh, okay. How many are living in terror the next 2 days? Oh, all right. Well, sorry to hear that. All right. Last questions. Going once. Going twice. Where are you from? Oh, I've heard of New Jersey. All right. So let's see what else we're going to do today. Where were we? All right. Last time we talked about pointers and linked lists. We talked about how to add a node to the list, which particular node adding did we do? Where did we add the node? To the front, yep, to the front, the head of the list rather than the tail or the end of the list. That meant when we printed the list came out backwards. We talked about how to traverse a list. This is the equivalent loop that we had. When you have a vector, you do, for I equals 0, I less than vector.size. For this, we have pointer current or temp or something like that equals head, while current or temp does not equal null. You can look at the thing and then you say current equals arrow current get next, and it'll move the pointer forward. And we looked at, for that list, how to do search based on that type of iteration, right? Didn't we? It's been a long time, I forget. And the other thing that this is useful for in case you ever need it is how to find the last node on a list. Like if you're working from the head of the list and you want to find the tail or the last node of the list, you iterate similarly until the node the pointer is pointing at does not have a value in the next pointer, is a null next pointer. All right, so today, I know this stuff is confusing, so we're going to do a few practice problems. Actually, one practice problem about nodes, and I'm going to show you how it kind of works and give you the solution, because there'll be a problem similar to this on the exam, which I believe is Thursday. Is that correct? No? Okay. And then we're going to start talking about something amazing. Okay? Something amazing, which we'll start today and we'll finish up on Thursday. All right? All right, so we're just going to do problems first, because why not? It's fun. And I have this sample problem. So this is something you can work in pairs, you can work in however you want. I would recommend you take a shot at it and see what you can get. And I will hand this out. Partner up. We haven't done this in a while, right? It's been busy, but. Pardon? We haven't done the code is right. Do you all miss that? Is it? I don't know if it's more fun or more terrifying. Yeah, that was my experiment this class. I kind of liked it, but anyway. With all the snow days we've had, this kind of class got out of whack for me. So, how many of y'all hated the code is right? Anybody hate it? One. How many of y'all liked it? How many of you are ambivalent? How many have no opinion? How many of y'all injured your arms? Should be 2 there, hopefully. All right, so go ahead. Why is it so quiet? Start talking. Read through the problem with someone. This is really a group exercise. Do whatever it takes this time. You have to do it by yourself later. It's a declaration. It's not a dereference. The same operator is used for different things, sadly, which is confusing, right? The star sometimes means dereferencing, but if it has a class name in front of it, that means you're declaring something.
So the space doesn't matter?
No.
Actually, I thought the space
So
mattered.
if it was just star pointer, that would be dereferencing the pointer and setting equal to null, but because there's a node in front of it, it's actually.
It's saying
Yeah, yeah. So we're creating two pointers right there. Nothing. Yeah, and that's the safe way to initialize pointers, just like that.
What is the W lecture? So we move pointer to
saying code current and change what change the data within change the data of the object that current is pointing to.
Exactly. And then the second line is just getting the data that
Yeah. It's not really that, well, it is confusing. It's true. I'm not going to lie. However, everything we've been doing throughout the semester leads up to this. It's not really any different than what we've been doing before. Okay? Where do you start? Where do you start a problem like this? Int main. And then what do? Just go step by step. Just go step by step. That's all there is to it. It's just now we're getting into a higher level of detail of what's going on than we'd had before. So. Not quite sure what you mean by that, but they are. It's just now you're manipulating things that don't have names, and you got to do it by address. And so we're kind of simulating what the address is because we know there's a new one. We don't know where it's addressed, but we know this thing over here has the address of this new thing, even without knowing quite what it is. Right? So it is confusing. I'm not going to lie. The first computer science I ever taught was pointers. I went out drinking with a friend before she had a test, and I kept her from studying pointers. So she's like, "You made me go out, so now you have to teach me pointers." I was like, so yeah, she's a neurosurgeon now. So yeah. Actually, I don't know that she passed, but she's still a neurosurgeon, and she has nothing to do with pointers. So. All right, we're going to take about 2 more minutes, unless everybody is sick of doing this now. You are. Who's ready? Who's not? All right. All right, well, more people are ready than not. So can you all actually see the code on the board when I do it this way? Is that okay? I just want more board space while I draw this than the little edge, so we'll call this like a fancy new teaching technology called overlays and transparency. All right. So every program, so this seems confusing, and I know it is, but it's just because you haven't quite made this the leap to realize that it's not any different than what we've been doing before. Okay? It looks confusing, it is confusing at first, but once you do it, you kind of just, we're doing exactly the same thing we've done before. All we're adding is that we have objects that don't have names that we have to get there. So when we start going through a problem like this, where do we start? Int main. Where is int main? Right up there. Okay, so we've hit the code with this first line, node star pointer equals null. What does node star pointer mean? Is this dereferencing something? Why is it not dereferencing something? Because it has a class in front of it. Node star pointer means that since it's a star, it's the address of a node. The variable is named pointer, and we're initializing it to say it's null. So here, pointer, and what is this pointing at? Null. And in fact, if you were going to look in there, it's actually 0. Like, it's a variable. Remember, an address is just a number, right? Is an int a number? Is an int a number? Are you happy about thinking about numbers living in memory? Yeah. All this is an int, and the int happens to be the address of something else, but it's still an int. It's just such a big int, we use hexadecimal to represent it. So what this is saying is that we have a pointer, and it's not pointing anything, or it has a 0 value. Everybody good with this step? Okay. Now we go on to the next line. What does the next line say? Node star current equals null. Is this a dereference? Why not? Because that has a class in front of it. That makes it a declaration of a pointer. What's the pointer's name? What does it point to? Nothing, so it's null. All right, now we reach point A, and on the exam, this would be the correct answer. It's pretty easy so far, isn't it? How many are happy? How many are unhappy? How many of you exist in some sort of other emotional state? Terror. Does terror work for you? Confusion. But does this make sense so far? How many of all this makes sense so far? What is not making sense if it doesn't make sense? Yes? So, no, so what happened? Okay, so the question is, what do you mean by point A? So here's what this means, and that's actually an excellent question because I did a bad job of describing what I mean. As this program executes, as we go from int main and execute down towards the return 0, there are things that are going to be happening in the computer memory. Right? Everybody good with that? What we're going to do is we're going to keep drawing what's going on in the computer memory. And when you reach one of these point A's, that means what is the current snapshot of the memory at that point. Okay? Does that make it easier? Okay, how many are less terrified now? Oh, well, good. That helped. All right, sorry, I've done this like 18 billion times. I take that for granted, so I should have done a better job explaining it. So we're building a model of memory. At point A, this is what our memory looks like. When we get into point B, we're going to want to know what that memory looks like at that stage. Does that make sense? All right, who's with me? Who's against me? All right. So I'm going to scroll the code up a little bit so like it's kind of on the white part of the board. Is that a little bit better? Sort of. All right, so we reach this for loop. For int I equals 0, I less than 7, I times equal 2. Have we seen for loops like this? Are you pretty comfortable looking at these now? Who wants to tell me what numbers this for loop is going to produce? Yes, sir. 1, 2, and 4. It'll start at 1. Multiply by 2, get 2. Multiply by 2, get 4. Multiply by 2, get 8. 8 is greater than 7. So we stop. So it's really 1, 2, and 4. So the first time through this loop, we're going to go through 1, 2, and 4. The first time through the loop, we go through with the value of 1. If pointer equals null. Is pointer equal to null? Okay. So what we do is we go into here and we say, aha, pointer equals new node I. What value is I? 1. Absolutely. What does the new keyword do? It creates a new object. This object doesn't have a name. It has an address. What's the value inside this object? 1. So we create it. We don't know where it is, but how do we keep track of where it is? Because now pointer equals new node means when we create this new node, we get an address back, and that address is now stored in the variable named PTR, pointer. So we created the new node, and pointer PTR is now pointing at it. What is this thing pointing at inside this new node? Why? Yeah, it's pointing at null because the class definition, when you create a new object, initializes it to null. I put in there at the top of the sheet, assume the node class definition is included here. On the exam, I will actually put the node class definition on the cover of the exam for you to refer to, if needed. I mean, the problem is that space-wise, if I dump the entire node class on one sheet of paper, it ends up like overflowing. And then if I have like 19 questions on nodes, I end up duplicating that code over and over. So I just put a copy for you to refer to. Okay, but for the most part, if you know that, you know, set data, set next, get data, get next, refer to those, that's pretty much mostly all you need. All right, everybody happy so far with this? Is this so horrible yet? Questions? So we've done this line, pointer equals new node I, and we created that. What do we do next? Current equals pointer. So what is current right now? It's not pointing at. What does current equal pointer do? Does this make current point at pointer? It makes it point at the address that's in there. So it ends up current is pointing exactly the same thing PTR is pointing at. All right, so we finished the if statement. Are we going to do the else statement? No, because we did one but not the other. We reach the bottom bracket and we go back up to the top of the loop. We are on the second iteration of the loop, and this time the value is 2. 2. Okay, So now we drop in and we say, okay, I is 2. If pointer is equal to null, is pointer equal to null? It is not. So where do we go? The else statement. I'm going to scroll the else statement up where we can see it. Uh-oh, this looks complicated, but it's not, okay? Yes? This is just my null pointer symbol. Here, you know what? I'm just going to write null here. So what this is that's a storage block, and that's storing the address of the next thing on the linked list. And what this means when you have a node that has a null address is that it is the end of the linked list. Yep, so current is pointing to the entire box, right? These things don't point to one of the things inside, they point to the entire object at once. All right, so now we're back in the loop. I is 2. We decided pointer is not equal to null, so we're going to do the else statement. So the first line, current arrow, current arrow, set next pointer, new node. And I'm sorry a little bit about this. I used a slightly different language in my node class here. This is like set next instead of set next pointer, but they're the same thing. What we're doing is setting the next pointer in here. Okay? So what we're saying is current arrow, set next pointer, new node I. How do we handle this? Sir? Uh-huh. So we say current, and then the arrow operator means follow the pointer, and we end up at this object here. And then what are we doing? Set next pointer method is changing what? Where this null is, and this is changing it to what? Okay, so what's happening is this null right there is being changed because we're creating a new node that has a value of what? 2, because that's I. And this thing is pointing at that object, and this new object is null inside there. Sir?
So when you change it, so the current set next pointer, since it's pointing at what pointer is pointing at?
What is it?
Since current is pointing at the object that pointer is pointing at?
Yes?
Does it technically change pointer at the same time?
Nope. So your question is, since current is pointing at the same thing pointer at, is it changing pointer at the same time? The value stored in pointer does not change. What changes is that these both are pointing at the object, and the value that's in that object changes. So your answer is yes. If we were to start following this from pointer, we would find that, in fact, this had changed as well. If you did pointer arrow get next, it would now have the new thing in it. Okay? What we're doing is with the addition of pointers, we're just manipulating numbers, right? Instead of ints, we have addresses, and so what we did is change this. Okay, so that one line, did that make sense to everybody? Yes? This is a pointer pointing to 2, and I just drew a dot with an arrow there indicating the pointer. In the real world, this is an address. It's a large hexadecimal address, and it happens to be the address where this other object is located. Current, at the end of this line, current arrow set next pointer new node I, we have not changed current because we have not done anything that says current equals anything, which is how we assign it. All right? Yes? Uh-huh. Yep.
Lists are connected because the objects in the list carry a piece of data and then the address of the next object.
Yes.
And that's how they're connected.
Yes. So the way that, just to for the recording's prosperity, in case anybody ever listens to this, even though it'll be useless because you can't see the diagram on the board, the way a linked list is created is that each object contains some data, but it also contains the location of the next object on the list. Okay? And so what we're doing is when we have a pointer, it points to the entire object, but within that object, accessible by a method, or settable by a method, is the location of the next thing on the list. All right, other questions? So to recap, this one line, current set next pointer, what we did is we got to current, the arrow operator meant follow the arrow. When we got there, we had an object. We said set next pointer, which changed this thing. And what it changed it to is the address of a new node that contained the value of 2. Okay? Now maybe what's confusing about pointers is that the notation is very compact, right? Like a lot of stuff happens on one line of code. It's not like you're setting things. So everybody with me on though? Current, find current, arrow means go there. When you get there, there's an object, call set next pointer on that object, set it to the address of a new node. The next line now says current equals current get next pointer. What are we doing here? We're changing the value of current because we have the equal sign, and what we're changing it to is you start at current, follow the arrow because we have the arrow operator, and say get next pointer. Where does this pointer here pointing at? The one down here containing node 2. So what ends up happening is current now points at the node containing 2, the value 2. What is the name of the node that contains the value 2? Doesn't have one. Does it have an address? Where can we find the address of this node containing 2? There's 2 places. Where? The current and the address of the node prior. Yes, sir. Yeah, so let's read this line. Current equals, this means that we're going to do something. And because with equals, just like every other assignment we're going to do, we're going to change the value of current. We're going to change it to current arrow get next pointer. So what it was before is it looked like this. Current was pointing to the node that contained 1. So here's what we do. We say current is going to be set equal to something. What we're going to set it equal to is current arrow get next pointer. So we start at current, follow the arrow. When we get there, we say get next pointer tells us what's in this box right here. And what's in here? The address of the next one. And so now we change current to the same thing as the next one right here. Yes? Uh-huh. Because that's actually part of the node class, which we've been talking about. And you see that big thing with stars up at the top? It said node class goes here. That's all part of the node class, which we've been talking about over the last few days. So I did not repeat the code in there. Does that make sense? So that's where that class stuff is coming from. Okay. All right. Everybody still happy? Or less happy? Unhappy? Confused? How are you? Less terrified? I'll settle for less terrified? No? Okay. All right. So we just finished this line. We finished the curly bracket of the else. We finished the curly bracket of the while loop. So where do we go? Back up to, the for loop. So we go back up to the for loop. We iterated once with 2, once with 1, once with 2. The next value is 4. So I is 4. We say if pointer equal null. Is this the case? It is not the case. So we're going to go to the else. And the else says current set next pointer new node I. How does this work? Help me out. Current, follow the header, get down here to the node that contains 2. Then what? Yep. So the address part, the next pointer part used to be null, but now it is pointing where? To a new node that contains 4. Everybody with me? So current, follow the arrow. When you get there, set the next pointer inside this object to a new node that contains a value of 4. Okay. Everybody happy with this step? Anybody not? All right, then we go on to the next step, which is current equals something. What are we setting current to? Current get next node. So what we do is we start at current. We use the arrow operator. We end up to the object that has 2. And we say, hey, where are you pointing at? What's the next pointer pointing at? And it says, oh, I'm pointing at this thing over 4, at this node that contains 4. So what happens to current? It now points to the node that has 4. Yes? Pardon? Pointer, essentially at the end of this loop, once pointer is set, it always stays the same. And it always points at the node that has 1 in it. Yes? Uh-huh. Yep. Yes. Exactly. So when we look at this diagram, we're drawing the box. The top of the box has the data. The next portion of the box has the pointer to the next thing. The way we access these things, because the box represents a node object, is by using the getNextPointer and setNextPointer methods, or the getData and setData methods. Okay. Everybody happy so far? Sir? We're almost at point B, but yes? Well, we're at point B, but we haven't officially said we're at point B. This would be exactly the... Nope. Now, is it easier for you to redraw things over and over and over? Yes, it is. But, you know. So now you've spoiled my thing. We move this pointer, we end the else, we end the while loop, we end the for loop because we're, you know, can't iterate anymore, and we're now at point B. So right now, this is what I would expect to see a picture of on the exam for being at point B. Okay? Does that make sense? This would be essentially the correct answer. Everybody good so far? Questions, please? Comments, criticisms, chit-chat. Well, maybe not chit-chat. All right, so we were at point B. We drew that and we're happy. Now we have a couple of things happening here, okay? That was the thing for point B. Now we have a couple of pointer steps. What does the first one do? Yes, sir. Uh-huh. Okay, so here's what we're doing. What you said was absolutely correct. Everybody laughed, but it was absolutely precisely correct. So we're changing current. It's going to be equal to something. And the thing it's going to be equal to is we start at pointer, we follow the arrow to get the arrow to that operator, right? Start at pointer, the arrow operator takes us to the node that contains 1. And then we say get next pointer, which gives us the pointer that points at 2, right? So what does current end up pointing at? The node that contains 2. So that just moves the pointer around. Nope. We did exactly what it says. Start at pointer, follow the arrow. We end up in an object. This object contains 1. We say get next pointer, and that takes us down to 2, and we're done. And we could have, you know, done like arrow get next pointer any number of times, but we only did 1. So now when we're done with this, current gets equal to 2. Everybody with me on that one? All right, what happens now? Next line. Sir, ma'am, how about ma'am? Uh-huh. Okay. So what happens is pointer equals current means pointer changes to point at exactly the same thing current does, which is the node that contains 2. Okay. Now, something else has happened here which you alluded to. How do we ever get back to node 1 right now? We cannot. It is gone. It is lost forever. We no longer have a pointer to anything that has a pointer to 1. It is lost. What is this called? A memory leak. If you ever end up in a situation where you no longer have a pointer to something that you can reach, it is called a memory leak. Okay? Because it's gone. Is this generally good or bad? Bad. What is your warning sign here that something bad is happening? We move pointer. So, before when we talked about linked lists, I had the head of the linked list named head. It doesn't always have to be named that. In this case, PTR pointer is the head of the linked list. When you see the head of the linked list being moved, it is generally a sign of danger. Bad. I just like bad. Yes, it's a sign of bad. All right? Except for 2 circumstances, which are creating the list or deleting the list. Okay. Yes? Okay, so the observation was, it looks like in this example, instead of adding nodes to the beginning of the list, we're adding them to the end of the list. And the answer is yes, that's exactly what we're doing. This is my, I'm trying to think of an appropriate term, my subtle way of introducing you to how to add things to the end of the list instead of the head of the list if you want. Okay? And the trick for adding things to the end of the list is that this current pointer could also, this could be called head and this one could be called tail, where current is essentially the end of the list. And that way when you add stuff, you already have found the end of the list and you can just add it there. Does that make sense? So when the exam, like, you know, for the midterm, I had the giant list of topics that came out for the exam. When the exam topics come out, you will see it will say know how to add things to the head of the list, which you talked about, and it will say know how to add things to the end of the list, which is this code right here. Yes, sir? Yes. The only time you erase the boxes is if we call it delete. Delete gets rid of the boxes. Nothing is pointing at it. And if I asked you where is the memory leak, your answer would be the node that has 1 inside of it. So point B is where we screw things up. And by the way, my exam question will be really similar to this. We'll create a list, we'll do some sort of horrible thing to it, and then after the horrible thing is done, you will tell me why it's horrible and what happened. Okay? That is point C right there, just like it is. No, but the exam question might explicitly say identify any memory leaks. Okay? It would be wrong to exit out at the moment, yes. But we're going to proceed on to a few other steps and see what happens. Okay? Sir? Yes, it does make a difference. In general. Well, I mean, you're doing different things, right? Depends what you want. Do you want things to come out backwards? Do you want them to come out forwards? Or do you not care? Well, you can, they're different things in my mind. So, and what's more common? Just, I don't know, whatever you want to be more common for you. So. All right, so everybody's happy with point C here. See what we've done? All right, here's what we're going to do now is something else. We have this while loop, and we say while pointer is not equal to null. And we ask ourselves, is pointer not equal to null? Yes, pointer is not equal to null. So now we have to go into this loop. And we say current equals, which means we're going to change current to something, current arrow get next pointer. So what happens here? We start at current. We follow the arrow to get next pointer. I'm sorry, we follow the arrow and we end up at the node that has 2 inside. We say get next pointer, which returns the pointer to 4. So we end up moving current from 2 to 4. All right? Does that make sense? We've done this type of pointer traversal a number of times so far. So current equals current, arrow, follow the arrow, get next pointer there. Now, cout, pointer, get data. What is this going to output? We start at pointer, follow the arrow. We end up at the node that has 2. We say get data, that's 2. So we output 2. Great. Now we delete pointer. What does delete do? It makes the object go away. So I'm going to indicate in this case by putting a big X through it. I could have erased it as well, but I'll just put a big X through it. That node 2 is gone. Okay. Everybody good with that? Yes, is when delete gets called. Delete means go away. Now, at this point in time, what is pointer pointing at? PTR pointing at? The answer is we don't know. It's pointing where something has been deleted. We don't know if the thing that was deleted is still there or not. Okay? When you have a pointer that's pointing off into random places that it's not supposed to be, it is called a dangling pointer because it points off just some place where it shouldn't be. Okay? Dangling pointer. All right. So now, the next line, pointer equals current. So what does this do? Pointer is no longer pointing at the node formerly known as 2, but is now pointing at the node that contains 4. Great, we go back up to the loop. Is pointer not equal to null? That's true. So we say current equals current get next pointer. So what happens to current? It turns into null. And here's why. Current equals current, follow the arrow, end up at the node that has 4 in it. Get next pointer is null. So what does current become? Null. Great. Cout pointer get data. So we follow pointer. We call get data on it, and we get what? 4. So we output 4. Then we delete the thing pointer is pointing at, which is a node that has 4 in it. It's gone. And then pointer equals current. So pointer becomes what? Null. Okay. So now we go back up to the loop. Is pointer not equal to null? So false, right? Pointer not equal to null is false. So the loop stops, we're at point D, and we're done. And this is what we end up with. And what we have is we have a memory leak where this node is gone. And this memory leak also happens to contain a dangling pointer because the pointer inside is pointing to a place where there is no longer anything. Yes? So when we delete pointer, that doesn't delete this. It deletes the thing it points at. So what delete means is go to that address, and when you get there, remove that object. Uh-huh. So current had already been changed to null by the time we changed it. So. Right, because we changed current to null on this first line right here. So just like anything in here, the things change. It's just stuff in memory. Just like a number will change if you use assignment or something like that, things change. And I've kind of lost track of which point in the process you're asking your question about. So I can't really say very easily. Uh-huh. At the end of the second iteration, current equals null. I don't remember. Was it? So at the first iteration, let's see. We already moved current to point here. So at the first iteration, we moved it to here. The second iteration, we made it null. So, all right. And now we're at point D, and that's what is left. So it would be pointer and current are both null, and then there is this one object that is a memory leak that isn't there anymore. All right, so just to help you out, I ran this on my computer. I drew it on every step of the way, and I also looked at all the addresses of everything. Okay? So if you're interested in going through this problem in detail and kind of seeing where everything is, I drew it for you in addition to what you might have drawn today in class. Because I like you. I want you to understand this. And you don't get one. You only get the questions. You have to pay for the answers. Actually, I'm pretty sure I don't have enough of these here. You might need one more. You want to pass one more back, just in case? What? Yes, of course. All right, so this is kind of as I drew it as I went along, if it helps. So. All right, any more? Anybody else need one? Extra copy? All right. So, that's pointers. That's what you need to know for the exam. Any last questions on pointers? Yes, sir.
That second one that we deleted, it's because we deleted it, there's no longer anything in there pointing somewhere, right? So there's no dangling pointer.
This one right here?
Yeah, the second.
Yeah, because it was deleted. I mean, this technically is really not such a dangling pointer because we can't get to it. Like if current or pointer were pointing off somewhere, something had been deleted, that would be worse than this because this one we can't even reach. So technically it's a dangling pointer, but we don't really have any way to get there. So, yes? So if we had at some point set another pointer to here and hadn't lost it, would we be able to find it again? Yes, but we didn't actually keep another pointer to this anywhere, so it's gone forever. Sir?
This is like completely hypothetical, but let's say we kept the pointer at 1 so it wasn't lost,
Okay.
and we deleted 2.
Yeah.
If we tried to print out the list, what would happen?
So the question is, say we had the linked list where pointer pointed at 1, 1 pointed at 2, two pointed at 4, and we deleted 2, and we tried to traverse the list and print. What would happen is it would print the first node correctly. When it reached the second node, the behavior would be undefined. One of two things could happen. Either when we deleted the node, it didn't actually overwrite the things in memory and the stuff was still there, which happens sometimes, in which case our program would execute correctly and it would look like the list was intact even though that thing had been deleted. The other option is that some other that memory was reclaimed by something else in our process, and when we went to print it out, we would print out something, and then we would follow some pointer somewhere, and then something else would happen, and generally that would be bad. So, but when we delete these things, I'll just tell you they happen to hang around in memory for a while, like for a while, which is why debugging pointers is hard, because you sometimes delete things and then you're like running through and it looks like you didn't delete it and you can still use it, and then all of a sudden it gets reused and it's gone. And this is some period after it's been deleted, so it's hard to associate the deletion with the fact that's there. So, all right. All right, 40-second break and place, stand up, jump up and down, stretch. You've been sitting down for a long time. All right, I'm going to hand out one more handout here. It's got two sides. We're going to do the side that says 1. And you know what? It's just some function calls. It should be relatively straightforward to you to give you a little mental break from dealing with this other stuff. Oops. Can you pass that back? Wait, where did I stop? Did you all get some? All right, so there's two problems on here. We're going to do the one on the front that says function calls. This should be relatively straightforward by now. Give you a little mental break, right? Did I already say that? So go ahead and do number 1. Don't do number 2 yet. We'll probably not get to number 2 until next class. So be sure to bring these back with you as well. So there's another handout we're working through. I just put it on your seat and it fell down. Should. Scroll down. They're optional. I almost always use them, but I forgot them for this. Here. There you go. If you only have one line there, you don't need the brackets, but you should just always put the brackets regardless of how many lines you have. But don't even. It's fine. I might. It's true. I'm not gonna do it on purpose to try and screw with you. It's just that I just forgot here. Yeah, I should probably mention that at some point. It's a safe programming practice to always use curly brackets. Do you remember the Apple bug that they had recently, like the security bug? I don't know if you heard about it. Anyway, there was a bug related to a similar programming thing like this. They had a particular call that, because there were no curly brackets, they thought was going to go to the prior line, but it went to the next line, so it always got called, even when it shouldn't have been. So. Well, you don't always need the code to find a security bug. There's a lot of different ways. So, but sometimes the program doesn't do what you expected. A lot of times, if your program crashes, that means there's a bug, and sometimes the bug is a security flaw. So some people use what's called a fuzzer, which is a program that just generates random input and feed random input to the program and wait for it to crash, and they see what input caused it to crash. And then based on that, they can reverse. Yeah. Yeah. And then once they figured out why it crashed, they can figure out why and see if it's a security bug. All right, so let's go ahead and get started on this. This is pretty simple, right? Everybody happy with this? Right, we're used to function calls now? How many of y'all are used to function calls? How many of y'all are giving me a horribly pained expression because I said you should be used to this? So, where do we start on this? Int main. What do we do in int main? Can I put the board up again? Do you mind? Does that sort of work or not work? Okay. Put the screen up. All right, so here's where we start. We start at int main. What do we do in int main? All right, so in int main, we set x equal to 3, and then what do? We call function 1. And what does 1 get in it? 3. So here I'm just going to draw. These boxes don't indicate objects. They just indicate functions this time. Okay? So main calls function 1. And inside function 1, we have something incoming, which is the name of the parameter equals 3. So what do we output? Entering 1. With 3. Now we call, now we're going to call 2, and we're going to pass it value 3, right? So, let's make my boxes smaller, I need a little more space. So, now we go down to here, and 2 has this variable named parameter. And we say entering 2 with 3, right? Now what do? Subtract 1, so 3 minus 1 is 2. So parameter in here switches from 3 to becomes 2. And then what do? If parameter is greater than 0, we say parameter equals 1 of parameter. So now we have to call function 1 again, right? And what do we call function 1 with? Okay, so now we get, enter 1 with 2. And what does function 1 do? It calls function 2. So it calls it with 2, so param equals 2. We say enter 2 with 2. And what happens to the parameter now? Subtract it, and it becomes 1. And then we say, is parameter greater than 0? Is it greater than 0? So what do? Call function 1 again. You all comfortable with this? Right? Every time we call these function, we get a new copy of the function. Okay, we're not calling the old one. Every time you call a function, you're getting essentially a new copy. So originally main called 1, 1 called 2, 2 called 1, 1 called 2. And now 2 is calling 1 again. And it says incoming is equal to 1. So now we say enter 1 with 1. Okay. And now what does 1 do? Calls 2. And it calls it with a parameter equal 1. And then what happens? Becomes 0. And then we say is parameter is equal to 0. Is it greater than 0? Oops, I missed one here. Okay, enter 2 with 1. Okay, so is parameter greater than 0? Is 0 greater than 0? It is not. So now we actually have to return something. Okay? We're going to exit. And what are we returning? We're returning parameter. So we're exiting and we're returning it with 0. When we exit, where do we go back to? This one up here? Where? The bottommost one. So when we return, we always return to where we were called from. So 2 returns to 1. And then we get back into 1 and we say, oh, well now we have this ret val. And we're saying exit in 1, returning ret val. And what's ret val? 0. So now we say exit 1 with 0. And now where does this one go? Where does 1 return to from here? Does it go back to main? It goes back to where it was called from, which is with this other copy of 2. Okay? So now we're down in here in 2, and we made this call, parameter equals, and so now we see out exiting 2. And what value are we returning? 0. And where does this 2 return to? The one before it, right? What are you all laughing about? Everything returned where it was called from. It doesn't skip just because this one called 2 doesn't return to a different one. It calls returns to exactly the copy it returned to. So we go 2 with 1, 2 with exit it with 0, exiting 1 with 0, exit 2 with 0, and this goes all the way back up until we get back to main. Okay. Yes? It will return 0 not to main, but it'll return 0 a number of times. Each time it returns to the one before it. So up here it'll return to that copy of 1 as 0. It'll return to this copy of 2 as 0. This copy of 1 is 0. This copy of 2 is 0. This copy of 1 was 0. And then to main it will return 0. Okay. Now, people are looking confused. You're asking yourself, why the hell would you ever do this? Is that what you're asking yourself? Why? What are you asking yourself? Okay. The point I want to make by doing this is not why we want to do that, and often I try to tell you why because it's easier to understand something with why. The point I'm trying to make here is, do you understand that when you call a function, if it calls another function, you get another copy of that function? Everybody good with that? So we have multiple copies of function 1 and multiple copies of function 2. You all comfortable with that? Great. See you Thursday. It's the start of something amazing. We'll finish up the amazing stuff on Thursday.